Alrighty, this video contains the solutions for the last two problems from your Physics So Far assignment. Alright, what do we have here? We have I'm just going to make a quick sketch. We've got bullet being fired of mass m, velocity v sub 0, being fired into block with mass m attached to spring with a spring constant, sometimes called a force constant, of k. And first part, we want to find the velocity of the bullet block system after the collision. And we know that this is going to be compressed 0.18 meters. Alright, so let's think about this. If we're compressing the spring that much, then we know energy here would be kinetic energy after that collision, and then the energy after the compression is all going to be stored in the spring, right? So I know that kinetic energy say at impact is equal to the maximum of the compression, right? So 1/2 m, they're both together now, v squared is equal to 1/2 kx squared. Well, let's go ahead and plug stuff in. 1/2, this is part A, sorry. Let's see, the mass of the bullet is 9 grams and the mass of the block is 1 kilogram, so the total mass would be 1.009 grams. And you notice here that if you left the bullet out, it makes a small difference, but we're going to include it because we should. And then 1/2, the spring constant is 300, and the maximum compression is 0.18 squared. So, for the purposes of calculation, those 1/2s cancel. So, looks like I should get, let's see, 300, well, I'm going to have to take the square root of the whole thing, right? So 300 times 0.18 squared divided by 1.009. That looks right. So that velocity is 3.10 meters per second. That's the velocity at the impact. We did that with energy. That was the way to do that. Now they want to know the velocity of the bullet before the collision. Well, now we're talking about before and after a collision, so that's momentum situation. So I know that the momentum before is equal to the total momentum before is equal to the total momentum after. What kind of collision is this? It's an inelastic collision because the objects are sticking together, but it doesn't matter because momentum is always conserved, right? Linear momentum is always conserved, at least as far as we know right now. And there is one situation where it's not, but that's for later chapters. All right, so momentum before is the bullet, the mass of the bullet times its initial velocity. That's the only thing moving. And then afterwards, we have the bullet and block going at this velocity v that we found here. So 0.009 times v sub 0, which is what we're looking for, is equal to 1.009 times the v that we found in part A. So the velocity of the bullet is 1.009 times 3.1 divided by 0.009. That's 348 meters per second, which seems like a bullet-like velocity, right? And then this is an inelastic collision, so we know energy will be lost, and they want us to figure out how much energy is lost. So we just need to figure out energy before and after the collision. So the energy loss will be equal to the final kinetic energy minus the initial kinetic energy. That's 1/2. The final kinetic energy is when the bullet and block are stuck together, and they're going at velocity v minus 1/2. Before the collision, it's just the bullet going at its v sub 0, which we found here. So we'll crank that out. It's 1/2, 1.009 times the velocity we found in part A, squared, sorry, oops, minus 1/2 the mass of the bullet times its velocity. And we expect that this is bigger, right? That the initial was bigger. So the change in kinetic energy should be a negative number, right? The 1/2s don't cancel here because we're finding actual energy values, right? There's no other side to cancel them with. Let's see what we get. 1/2 times 1.009 times 3.1 squared minus 1/2 times 0.009 times 348 squared. A negative 540 joules. That's the change in kinetic energy. They said how much energy is lost. So the answer to that really properly would be 540 joules are lost, right? We're replacing our negative sign here with stating that it's an energy loss. Right. That's a handy little problem. And last, we have another collision. So I'm expecting more momentum kind of stuff here. Got a heavy block of mass 4.5 kilograms. It's initially at rest at the edge of a 1.2 meter high frictionless table. If you happen to see one of those at a garage sale or a flea market or something, I would love to have one, a frictionless table. Don't right now. The table has a length of 2 meters. A light block of mass 0.4 kilograms slides across the table at a speed of 25 meters per second and strikes block B, causing block B to leave the table in the direction in which block A was moving. Makes sense. The figure below shows a graph of the force exerted on block B by block A as a function of time. So as soon as we see this graph here, we should be thinking, hey, this is a force versus time graph, and the area under a force versus time graph is equal to impulse, which is equal to change in momentum. So if we can find the area under this, and also the other thing I would say, this is true in calculus and physics also, is when we see a graph that looks so geometric like this, it really kind of calls out to us, cries out even, that we might be wanting to take the area under this. So I'm going to go ahead and do that. And I'm going to be very careful here, watching these units, right? That this here, and I think that this is 10 to the third, 10 to the negative third. You might get away with if you didn't do this, because I think those will just cancel, but this 4 here, so this is really 4 times 10 to the negative third. And this height here is really 2,000. So I need the area of this triangle. 1/2 base times height. 1/2. The base is 4 times 10 to the negative third times height. That's 4. Yeah, you would have got away with it. And it's kind of unfortunate that they let us do that. And the newtons, the units would be newtons times seconds. And we know that newtons times seconds that's one of the ways we can write the units for momentum. All right. This is symmetric, so that's also 4 of those. And then this, now that we know that we can cheat here, this is 2 by 2. This is also 4 Newton seconds. And that makes sense. If you lopped this off and put it on there, it would be the same as this rectangle. So the total change in momentum, determine the total impulse given to block B. Well, we just did that, didn't we? So for part A is, and I'm going to be very explicit about what we did here. The impulse is equal to the area, the force, and you probably get away with not putting anything here, but in fact it's from 0 to 10 to the negative 10 times 10 to the negative third seconds. That is equal to 12 Newton seconds, or kilogram meters per second. You could write it that way too. So that's the impulse. Okay. Determine the horizontal velocity of block B immediately after the collision. Well, impulse is equal to change in momentum. So 12 Newton seconds is equal to the final momentum minus the initial momentum, right? But of course, block B is at rest to start, so this is just a 0. Sometimes scientists do this. You just write it like, oh yeah, that's a 0. So 12 equals, momentum is mass times velocity, so the mass of that block was 4.5 times its velocity after the collision. So that's 12 divided by 4.5, 2.67. And then in part C, determine the following for block A immediately after the collision. They want to know what's its speed and what is its direction of travel, moving left or right, or if it's moving at all. So this is a collision. I don't really know what kind because they didn't say, but I know that the total, sorry, that's a wrong symbol there, the total momentum before the collision is equal to the total momentum after the collision. So before the collision, block A is moving, mass of A times its velocity, and I think I know those things, right? And then after the collision, the mass of block B, I'll call that initial velocity there. There's going to be a few V's over here. So then the mass of block A, whatever its final velocity is, plus the mass of block B times whatever its velocity is. Those, I've written VF for both of those. Those are not the same velocity, right? This is this one. That's the velocity of block B. All right, so let's throw things down here and see what we can get. So mass of block A times its velocity before the collision, which we know is 25. They told us that. Mass of block A times its final velocity, that's what we're looking for. Mass of block B, 4.5 times its final velocity. Of course, this is the momentum, so I could have just used the 12. This is going to be that 12 number, right? The momentum of block B after the collision is equal to its impulse. So that's going to be 12, right? So looks like I'm going to have to do 0.4 times 25 minus 12. It's negative 2 divided by 0.4. So negative 5. And they asked for its speed and its direction. So in part 1, its speed is 5 meters per second. And in part 2, the direction is to the left. Right, that's what that negative sign means. Right? And it shouldn't be a big surprise that it rebounded off that block, since that block was much heavier, right? So it did rebound off that block. If block A had been heavier, then it would continue going in the same direction. All right. Determine the kinetic energy that's dissipated in the collision. So let's find the change in kinetic energy. That's equal to the final kinetic energy minus the initial kinetic energy. And notice here that the final kinetic energy, there's two things moving, right? And the initial, there's only one thing moving, so just be careful with that. So the final kinetic energy is 1/2 mass of block A times its final velocity squared plus 1/2 mass of block B times its final velocity squared minus 1/2 mass of block A times its initial velocity squared. Right? That's the energy after, that's the energy before. And just like in the last problem, we're expecting to get a negative number here. 1/2 mass of block A times its final velocity, which is -5. Of course, it doesn't matter the negative because I'm squaring it. Kinetic energy cannot be negative. 1/2 mass of block B times its final velocity, which we found up here, minus 1/2 mass of block A times the initial velocity of block A, which was 25 squared. And like the last problem, the 1/2s do not cancel out because we're actually calculating the energy here. And let's jam that all in there and see what we get. I dropped that negative sign because I'm squaring it anyway, right? I knew that would go away. All right, let me just check, make sure that's right. 0.5, 4.5. Looks like I got it in there right. Expecting a negative number. So it's a negative 104 joules. So 104 joules of energy lost in that collision. So it was not a perfect elastic collision. Kinetic energy was not conserved. And then determine the distance between the 2 points of impact of the blocks with the floor. So we have to do two kinematics problems here. This is a cute little problem here, I think. Good practice for kinematics, but also just for thinking. When the block A rebounded, so when it leaves the table, it's going to be going this way. at 5 meters per second. When block B leaves the table right after the collision, it's going to be going this way at 2.67 meters per second. So I need to find this impact, and then I also need to keep in mind that this distance right here between them on the table is 2 meters. So I'll have to add that in. Right? So it's going to be this distance plus 2 meters plus that distance. That's how far apart they're going to land from each other. Okay, so for block A, we have it. I'm going to ignore the negative sign here. I'm just going to find this distance as if that's the positive direction. So I'm interested in this positive distance. So the vertical part of that problem, initial vertical velocity is, think about it, it's 0 because it's a horizontal launch. And the acceleration is negative g, and it's going to have a delta y of negative 1.2 meters. And I'd like to know the time, so I can bring that over to the horizontal side, where it has an initial, or a constant horizontal velocity, rather, of 5 meters per second. So here, our old friend, delta y is equal to 1/2 at squared plus vit. But the vit is going to be 0. So delta y is equal to 1/2 a t squared. So I need the square root of 1.2 over 4.9. So that's about 0.495 seconds. It should be about 2.5 meters, right? So to get the delta x here, multiply those two together. Times 5, 2.48, let's call it. Right, if you go 5 meters a second for half a second, then you got half of 5. Okay, so that's this distance, 2.48 meters. And then this one over here. You might think just real quickly, will this distance be more or less? What does that depend on? And these are projectiles, so the mass doesn't come into play here. So since this one's not going as fast, we would expect this is going to be a smaller distance. Let's find it. And the calculations are going to play out exactly the same way. So initial velocity is 0 because it's a horizontal launch. That's all horizontal. Acceleration is negative g. The delta y, once again, is negative 1.2 meters. And I'm just going to jump right down to finding the time, which I will do in exactly the same way. It's going to be, in fact, it's going to be the same amount of time, right? Because all those numbers are exactly the same. So 0.495 seconds. That makes sense. Oops, that doesn't make sense. That makes sense. Remember that a horizontal launch, something launched horizontally, will be in flight for the exact same amount of time as something that's dropped from that height, because that only depends on the vertical part, and the initial vertical velocity is 0. Remember, the bullet fired, bullet dropped. Time is the same, and this is 2.67, so I just have half of that, which should be about 1.34 or 1.35, something like that. 0.495 times 2.67, 0.13, or 0.132 rather. Right, a little bit less. 1.32. So distance between blocks at their landing is 2.48 meters plus 2 meters. That's the length of the table, plus 1.32 meters, which is 5.80 meters. What a bunch of good problems those were.